Good day to you, ladies and gentlemen. The title of my talk today is Multi-axial Real-Time Hybrid Simulation Testing. This is an experimental testing method for simulating the behavior of structures under various natural and synthetic excitations. Here is an outline of my presentation. I will lay out the motivation for my research. I will then present some methodologies that I use in my research, as well as presenting the experimental results. And finally, I will discuss some concluding remarks. In the United States, when it comes to natural hazards, every state is exposed to one or more of a host of hazards. Natural hazards can undo years of development and devastate the infrastructure. As it pertains to the infrastructure, earthquakes, tornadoes, and hurricanes are most notable. In the US, earthquakes cause over $6 billion in damages distributed annually, while tornadoes and hurricane losses amount to over $20 billion a year. This here is a map of the US population center, and I am going to overlap it with a map of the earthquake hazards map, and then I will show you the same US population center map and overlap it with the tornado and hurricane hazard map. So in civil engineering, we like to perform testing to make sure structures we design are safe and resilient. Hybrid simulation is a common testing method employed in many laboratories. A hybrid test is typically comprised of both numerical and physical substructures. A complete structure here is broken down into numerical and physical components, and at each time step, the boundary conditions like displacements and rotations are calculated. Actuators are then used to impose these boundary conditions on the physical specimen, and we also have sensors such as load cells, which are able to pick up relevant information like forces and then feed them back to the numerical model. This method allows for flexibility, space, and cost savings, and has proven to be repeatable over the years. Now, many areas of expansion have been explored, including real-time implementation, multi-axial testing, and sophisticated substructuring. With real-time testing, challenges include actuator compensation for reference tracking and stability. With multi-axial motion, mechanical coupling and geometric nonlinearities tend to kick in, and sensing and measurement also becomes much more challenging. And for substructuring, issues of having multiple boundary interfaces and having multiple physical specimen which could potentially interact need to be addressed. So I proposed my multi-axial real-time hybrid simulation framework to address many of these research gaps and challenges. The first challenge is the problem of multi-actuator motion. Whenever actuators are connected by a rigid link, they start to interact with each other. Because each of them have minds of their own, when just one of them is pulled or pushed, all the other ones are pulled or pushed as well. The geometry of motion between these actuators is also heavily nonlinear, and this makes the task of compensating much more challenging. The first step in tackling the problem is kinematic transformation, which means geometry of motion. So here I am showing a load on boundary condition box for illustration, which is comprised of a fixed base, a moving platform, and several prismatic limbs. When we add a physical specimen and potentiometers for displacement measurements, we get something that looks like this. In this context, kinematic transformation is the process of going to and from Cartesian coordinates from the actuator or potentiometer coordinates. So inverse kinematics is going from linear coordinates to Cartesian, and forward kinematics is going from Cartesian to linear. There is mathematics behind all these processes. So we have inverse kinematics, which is pretty much adding and subtracting three-dimensional vectors in space. And we have a forward kinematics process, which is much more challenging, involving solutions to several implicit nonlinear equations of motion, which we typically just linearize. Another step in tackling the discussed challenge is to have a model of the load and boundary condition box system. So here we do system identification, which is a process of identifying a dynamical model of the actuator specimen setup. What we can do is we can vibrate an actuator and record the command and measured vibrations. We then convert our time history signals to frequency domain through Fourier transform. And in frequency domain, we are able to describe the relationship between the command and measurements through a frequency response function. The frequency response function can be estimated via different methods. I used in my own research the H1 or the H2 method. The outcome of the described system ID process is a transfer function model, which again is another way of representing a model in frequency domain. I basically take my frequency response function and fit it with a transfer function model that I've identified, shown here. For a 6-actuator system, the frequency response function is a system of 6 by 6 frequency response functions. The diagonal term here refers to the relationship between the input to an actuator and the measurement from the actuator, and the off-diagonal terms refer to the coupling between the individual actuators. The off-diagonal terms here were found to be less significant. Therefore, by going from Cartesian coordinates all the way to actuator coordinates, we found that we can effectively decouple this system. The next challenge involves how actuators add unwanted dynamics to the experiment. The unwanted dynamics is felt most in the form of delays between the command and measured signals. Another easy way of seeing actuator delays is by looking at the hysteretic behavior of the actuator in the linear range, where an ellipse is formed with the area of the ellipse indicating the negative damping present or added to the experiment, which pretty much serves to amplify energy and cause instabilities. Therefore, we need to have control algorithms which are then able to compensate for the unwanted dynamics of the actuators. My solution to this problem is to take advantage of the decoupling we discovered earlier and to compensate for actuators in the actuator frame of reference. So I introduced my modified model-based controller. Here we have multiple blocks. We have the actuator dynamics. There is a feed-forward controller, which is an inverse of the actuator dynamics. There is also a feedback controller, which is a knowledge-based and error-based controller, and together these serve to compensate for the unwanted dynamics that appear in actuators. Another challenge is the difficulty of working with multiple boundary interfaces. For instance, ensuring that the boundaries in the substructured elements correspond to the domain and boundaries in the original structure. This can be a challenging task, and this is what I wanted to address next. To tackle this problem, I introduced my multi-axial real-time hybrid simulation framework. Here we have some excitation force entering our numerical substructure. There are one or more physical substructures which could be interacting potentially. There are transformation layers between the physical and the numerical substructures which ensure accurate calculations, execution of the boundary conditions, and return of the actuator forces back to the numerical substructure. This part is also computational. Now, all of this is done at real time at very rapid frequencies of 1,000 hertz or more. So some of the literature that came out of these studies is listed here. In terms of the hardware that's needed to run this kind of experimentation, it starts with a host PC. We can simulate everything in MATLAB, convert to C++, and send our application to a controller for execution. The controller will communicate with a servo controller for the operation of the actuators. And following the operation of the actuators, in this case, we have two load and boundary condition boxes. Sensor measurements are returned to the controller to pretty much close the loop. So I used two boundary condition boxes for my research, and these boxes were running with a pump supply of 10 gallons per minute at 3000 psi. To prove the proposed RTHS framework, I assembled an illustrative example involving an asymmetric four-span curved bridge subject to seismic excitations. With this experiment, we test two physical specimens and numerically model the rest of the structure. So this here is a video of one of our experiments. On the left we have the numerical substructure, and on the right we have the experimental one. These are the nonlinear dynamical results from one of the boundary condition boxes we have, and we were able to get accurate and stable results. In conclusion, we used a model-based compensator to allow for efficient removal of undesirable actuator behaviors. We manipulated each actuator independently in the actuator frame of reference. This was called decoupled control. This allowed for rapid realization of the 3D interactions we were looking for. Kinematic transformations, actuator compensations, and all the fast computational capabilities we had allowed for accurate realization of the dynamical coupling between the numerical and physical substructures that we had. So this was the MARTHS framework that I proposed with multiple boundary points. It extends the range of applicability for the hybrid simulation methodology. And lastly, I thank you for your time. If you have any questions, any feedback, you can find my email down below. Thank you so much.